In this video, we're going to be looking at linear second order differential equations with constant coefficients in the form a d2y by dx squared plus b dy by dx plus cy is equal to 0, where a, b and c are constants. And in this particular video, we're going to consider the scenario where b squared minus 4ac is strictly greater than 0. And this will give us now two distinct real roots. If we consider a solution to this differential equation to be in the form y is equal to ae to the mx, if we take the derivative dy by dx, we will have now a m e to the mx. The second derivative d2y by dx squared will be equal to a m squared e to the mx. If I put this back in, so substitute it back into my differential equation, I'm going to have a d2y by dx squared we can now put in as a m squared e to the mx plus b dy dx, so that's going to be now a m e to the mx plus cy, which is now going to be a e to the mx, and that is equal to 0. Taking a common factor of a e to the mx out, we get a e to the mx. We'll have now what's left, am squared plus bm plus c is equal to 0. We know a e to the mx can never be equal to 0. Therefore, am squared plus bm plus c is equal to 0. And this, if you look at it, is very similar to our differential equation here, and we call this the auxiliary equation. When we solve the auxiliary equation, and we have, in this case, two distinct real roots, m is equal to alpha, and or m is equal to beta, where alpha does not equal beta, the solutions to our differential equation will be y is equal to a e to the alpha x plus b e to the beta x, where a and b are arbitrary constants. So this is the general solution. So the take-home message is we solve the auxiliary equation, we find the roots of the auxiliary equation, and then we put those into the form y is equal to some arbitrary constant e to that root, and then multiply it by the x. We're looking when we've got two distinct real roots. In the later videos we'll look where we've got a repeated root and when we have either purely imaginary or complex roots. So let's look at a couple of examples. We're asked to find the general solution of each of the following differential equations. So if we consider this is again put in the form a d2y by dx squared plus b dy by dx plus cy is equal to 0. In this case, a is going to be equal to 1, b is going to be equal to 5, and c is going to be equal to 6. And of course, we know now that am squared plus bm plus c equals 0, the auxiliary equation will allow us to find those values of m. So we've got now m squared plus 5m plus 6 is equal to 0. So factoring m plus 2, what we're going to have, m plus 2, m plus 3, that looks good. So we can say now that the solutions to the auxiliary equation are m is equal to negative 2 or m is equal to negative 3. Therefore, the general solution to my second order differential equation is y is equal to e to the negative 3x plus b e to the negative 2x, where a and b are arbitrary constants. So nice and straightforward. That's all we need to do. If we consider the next one, we've got d2y by dx squared minus 8dy dx plus 12y. We can simply write now the auxiliary equation as m squared minus 8m plus 12 is equal to 0. That looks like it'll factor. What we're going to have, m minus 2 and then m minus 6 will be equal to 0. So we can say m is going to be equal to 2 or m is going to be equal to 6. So the solution, and the general solution that is, will be y is equal to a e to the 6x plus b e to the 2x, where a and b are arbitrary constants. and this gives rise now to these two constants. When we have a second order differential equation in this form, we will have two arbitrary constants. So there we go, brief intro. What we'll start to look at are a couple more examples in the next video, and then we will go on to look at examples where we have repeated roots and then either purely imaginary or complex roots.